Thank you very much. So, yes, I'm Colin, and I feel actually quite at home here in Amsterdam, even though I'm from Canada. And this picture is, just to be sure, this is not a ninja. This is actually me. And that is snow in the background. So, but I do bike regularly, so I do feel somewhat at home here. Just a shameless plug, actually, before we get going. High Performance Images. I'm one of the fellow authors on the book. And so at the end, if there are a few questions, I do have 3 free copies to give away, so we can use that as an incentive. So I mentioned that I was from Canada. So if any of you come to Canada, we might go out for drinks and maybe get some wings. I really do like good, sticky, saucy wings. Now, if we were to sit down at the table and the waiter comes, gets our order, brings us some wings, and at some point in the night, I'm going to realize that I've got it all over my face and my hands, and I'm going to look somewhat like my boy, food everywhere, and I'm going to think, I need some napkins. So I'm going to flag down the waiter or the waitress and say, hey, could you get me some napkins? Now, if they're a good waiter, those napkins would have already been dropped off covertly, discreetly at the table, and I would be able to use them right away without having to wait and wonder what I'm going to do. Like, do I pick up my beer and get it all over? So if they were a good waiter, they would have had this already, and I wouldn't have had to wait. And this is what we're going to talk about today, that opportunity of getting stuff before you know you need it. Now, push is part of the big talks that we're hearing about this week. How many people were at Yoav's talk yesterday? A few hands. And at Kazahu's talk? All right. So some of the stuff you might hear again, and I want to bring a practical level to this conversation, because we realize that when we look at a histogram of performance, of what our users are, we often see a big discrepancy between the 90th and the 50th percentile, when in fact we're trying to hit this barrier of maybe a 2-second performance load. 2 seconds being the magic number where we know we've got the user's attention. And so there's a lot of different tricks in our toolbox. We typically start to look at the web page test waterfall and start inspecting, looking for the culprits, and even looking down at the bandwidth at the very bottom and the CPU utilization. Now, the tricks that we have up our sleeves, you're very familiar with them, reducing the number of bits across the wire, reducing the number of requests, increasing the performance on the browser, and even things we can do to bring the content there faster. We can use a time machine. Because if you've got the opportunity to use time travel, you have to use time travel, because then you'd go back to the 90s and have a little salt and pepper. Just push it. Oh. All right. So we've looked at the time to first byte in a sample set at Akamai, and we looked at how long does it take for the first byte of that HTML to get to the user? And in the sample set, you can see that 50% of the time, so this is a cumulative distribution function, so the left-hand side is your percentile, so 50% of the time, the user has to wait at minimum 450 milliseconds. So if you're looking at a 2-second performance budget, that's 25% of your time spent just waiting to get bits to the device. And so this is where we want to spend our time. And there's obviously many reasons why the long tail could occur. And it could be because of your infrastructure. It also could be because a person is sitting in a big Faraday cage, like many of our offices. So I'm going to show you a tool later on how to look at your own bandwidth and the web page test results, because we want to focus on this area of waste and how much opportunity can we use to improve the performance. Because if we can get it right, we can use time travel and get resources to the user sooner and get that user experience so much faster. Now, you might be rightly asking, well, haven't we already solved this idea of push? Like, it's 2016. Shouldn't we have figured out how to do push? Well, you're right. There have been a number of different attempts and different technologies that are available to us. So just quickly, there was the old school polling, which would basically sit in the TCP, HTTP stack and just sit there, give me part of the response, the headers, and just sit there until you get the final response later on. The downside here is that if you did that kind of push, it's not really a push. You're just causing the browser to spin its wheel. Now, we've got another technology that's probably more apt called WebSockets. It has the word web in it, so it's got to be cool. WebSockets are great, but they're not meant for many to one. They're not meant for caching. They're meant for a one-to-one relationship where you've got an app and you want to stream it because it goes back to your infrastructure. So it's not that great for pushing content that's meant for the web. It's really more like a socket sitting on the web. WebSocket, yeah. All right, so there's also WebRTC. You may have heard of it. Really, it's just similar to WebSocket, similar APIs, but it's really just for communication. It's not, yes, it is pushing content to and from users, but it's media. So it's not what we're talking about. And finally, there is this idea of server-side events, part of the HTML5 spec, in fact. And server-side events do give us the opportunity to push content to users. And as you push it, you can get notifications in your code. But this requires JavaScript and requires it to be already spun up. And it's also only text-based. So it's not really solving the problem we're trying to address, of trying to get some of that critical rendering stuff, JavaScript and CSS, to the user sooner. And so this is where HTTP2 starts to come in. Now, the first challenge that we have with HTTP2, or in HTTP in general, is the slow start. So just a quick 101, if you recall, the device makes a request, the server sends back some content, but it's got only part of the content, and the client has to say, I acknowledge it, and then it sends double the content back. So that's, every time you do an acknowledge, you get 2 packets back. Now, if I were to look at the standard HTTP archive, look at wherever our content is, images, style sheets, we can see that we've got about almost 500K in style sheets and scripts, 50K in HTML. So if I were to use a standard mechanism, I would see, it would take me actually 3 round trips to get just the HTML. And I'm using an assumption here of 50 milliseconds, or sorry, 100 millisecond round trip time. And because the first packets that come back are 10 packets wide, so about 14K, well, I've got 50K to go, so I've got to do it in the next chunk, so it's now 48K. And now I need to do, 20 packets, and then I got to do another 8 packets to finish it up. Then the browser has to figure out what it's got to do, and then start making requests for your JavaScript and CSS. But you do see this incline, this ramp, as the packets start to accumulate, and you start to be able to send more and more data. So this gap in the beginning here is the time to first byte, and the gap to the right is the time to first resource. But if we can use HTTP2 push, we can push that content earlier. We still have to be subject to the laws of physics and the way that TCP works, but we're able to push some of the bits for our JavaScript and CSS early and get the HTML theoretically where it's supposed to be, and then finish off with the rest of the JavaScript and CSS. Now, this is a theoretical model that I'm showing you here with TCP slow start. The objective, though, is to warm up the connection earlier. Now, reality, of course, anybody that's looking at congestion windows will argue, well, it's not so clean. But we'll ignore that for now. We'll talk about that a little bit later. So HTTP2 brings us a number of things. Just to quickly highlight the set of tools we have here, there's really 5 different pieces of data when it comes to the HTTP2 push. First off, there is the settings, which happens at the HTTP connection. And by default, browsers are forced into enabling support for HTTP2 push. They have to opt out intentionally. So if they send the settings frame at the beginning to say that they opt out, that's the end. Then, of course, there is the push promise that comes from the server. And the push promise frame is just a headers frame that contains what the request would have looked like had the user made the request in the first place, followed by headers, which is the response, and data. Now, of course, there's also the reset stream if the device said, hey, I don't want you to push me this content. So an expected life cycle should look something like this. The device makes a request. This is using the headers frame, but it makes a request saying I want slash. And at this point, the server is going to respond. Now, you'll see there's some numbers here. The promises are on, in this case, stream ID 2. Streams are odd if they're coming from the client and even if they're coming from the server. So it says I'm going to push some content, and it waits a little bit and then sends the headers related to that promise. And then the data, and then followed by, later on, the headers and data from the original request that you get. Now, if the browser decided, hey, I don't want you to push that content, then you get this reset stream, and the device would say, I'm out, I don't want you to push that content. And then the rest of the regular cadence of the request would go from there. And if you're using NGHTTP, you might be familiar with some of these. The way it marks it up, you'll see the settings there and the reset stream. So NGHTTP, as well as other tools, will start to expose some of these details. So the first question I started to wonder about is, all right, so HTTP, good, I see the opportunity, see the potential, but can I push? How do browsers interpret the various attributes of push? So let me just quickly summarize how the browsers basically all function. There is, the device, the user makes a request, and inside the browser, it's got its own cache, and there's a secret queue that sits behind it. Now, Yoav will say, well, that's not true. It's neither secret nor a queue, but otherwise, it's accurate, I suppose. All right, so let's call it the unused streams. There you go, I got the thumbs up. All right, and now this is what's going to broker the stream request coming from your application server. So in this case, the browser actually receives streams for the HTML and the CSS. But when it's rendering it, it only needed the HTML. Later on, as the rendering engine, the tab is ready to start processing the CSS, it didn't need to actually go to the server. It already had the CSS, and it picked up the content. All right, so that sounds like it meets what I expect. It's got this little, there's another device, another entity in there for the unused streams, but all right, I get it. And if you're looking inside of your browser, if you're looking inside, you'll probably see something like this in your timeline. You'll see at the very bottom, you see that you've got your typical response headers and request headers. And you'll notice that down here it says provisional headers. Now that means that this browser did not send the request headers. This was what was given to me, telling me what I would have sent. So you'll usually see less content in the headers, because it's the server making a best estimate, user agent, accepts, refer, if possibly the refer, and sending that content to the browser. And so that's what you're going to see when you see that provisional content. And one last piece, in the browser, you'll also see that in the timeline, you'll have the receive push. The receive push indicating that I received it earlier than I actually started needing it to calculate my rendering flow. One last little tidbit here. If you're using Chrome, it's actually pretty easy to start seeing the content underneath the hood. There is the net internals, and you can start seeing. Now, they look like HTTP2 frames. It's actually just debug headers, but you can get a good sense of what's actually going on under the hood. It's a little more difficult and contrived in Firefox, but you do have some of that data. And Safari, well, it's Safari. Now, there is one other thing to identify here. You'll notice in inside of Chrome that there'll be adopted streams. You'll see when the browser makes the adoption. If you're pulling up a request in web page test, you'll see all of the requests, whether they're pushed, regardless of whether they were adopted or not. You do have this diagnostic at the bottom that says how many were unclaimed, because you have the possibility of the server sending content that isn't actually used by the device. The device may have, for a number of reasons, decided not to use it. And they're going to be sticking around for about 5 minutes. That's why it's not quite a cache, it's not quite a queue. It sits there until you would use it. If you don't use it, it just disappears, gets garbage collected, and away it goes. So this brings me back to well, I can play in Chrome, I can see the diagnostics. Do all browsers behave equally? And so I want to introduce you to a tool called Can I Push? Because what I want to do is I want to build a harness around HTTP2 and see how different browsers behave. Because perhaps they aren't all using the same interpretation of the spec. So what I'm going to do, and I'm going to show you a few steps here. Some of you, I can see you just typing in, and you're already like 5 slides ahead of me here. I'm going to actually use different responses if it's requested by the browser or if I'm pushing it. And I'm going to test the different responses to see how the browser behaved. And with that different content, then I can give you a nice report. So let's start with the basics. All right. So HTTP2 works. And in this case, I'm just going to test connection coalescing, meaning that I'm using the same socket, the same client port for both the on-domain requests, so www, as well as if I use domain sharding for some of my resources, so maybe it's called images1 dot, they're going to collapse to the same TCP socket because they use the same certificate and they're on the same server. So in this case, success. All right. Let's go one more step here and test it. Ooh, that's unfortunate. You see that while my Chrome browser does connection coalescing for CSS and JavaScript, it failed for XHR calls, XML HTTP requests. And it failed because the browser wasn't quite sure if this domain actually honors cores. And there are separate sockets maintained for XHR calls. And because of this concern, the browser decides not to use the connection coalescing. It'll open a new request for those API calls you're making. So, okay, that's interesting about HTTP2 in general, but what about push? All right, well, let's just take a quick gander at how the browsers do before we get there. All right, Safari. Well, that's unfortunate. All right, so that's just Safari 10 running on El Capitan. What about modern? All right, Safari 10. All right, well, you don't do connection coalescing. Safari you do. Firefox you do. And Edge, you don't do it today. Well, but Edge is supposedly coming soon, so they do want to do it. So we'll see when that comes. So we've got 2 browsers out of the 4 that do connection coalescing. Let's start with a simple push. Now what I'm going to do is I'm going to push the same resources, JavaScript, CSS, and do an API call on the device. All right, that's awesome. Now what's interesting here is that I'm doing an XHR call as well. So an API call, but it's on the same domain. This is all on the domain. And so far, she looks pretty successful. And if we look at the browsers, Safari, great. Chrome, great. Firefox, great. And Internet Explorer, or Edge. Now notice that Edge treats the XHR call with the same kind of scrutiny. It does not allow the XHR call to be pushed for APIs. But all the other browsers do. All right, so let's move on to the next item of business here. What about those sharded resources? Now, this is an important aspect for many of us that are evolving our websites are websites that do use domain sharding for CSS and JavaScript, and I've unfortunately am handcuffed in how what I can do. And so I do want to move. I've got a lot of legacy clients that I need to have sharding, but what if I can shard and push? I get the best of all worlds if I can do some connection coalescing. Clicky click. There we go. And what do we get? Oh, OK. So it's similar to what we expected in the connection coalescing. I'm able to successfully push shared resources for JavaScript and CSS across domains. But of course, our API calls, they fall flat. And this is fairly consistent across our browsers as well. Well, of course, Safari doesn't support connection coalescing, so it rejects them all. Chrome doesn't allow it. But you see, Firefox also doesn't allow any, even though it supports connection coalescing, it doesn't support any other domain for pushes, because it looks at a very simple model of like, does the host and the port match? If they don't match, I won't accept any pushes. So already we start to see the chinks in the armor here. And of course, Edge, which doesn't support coalescing, also rejects those items. All right, so we know that for the most part, push for Chrome and for Chrome across domains works. Everybody else, it's dicey. What about different certs? This is an experiment of like, well, what about Chrome? What if if I push something it shouldn't accept? Something from maybe on my website, I'm going to push content for Facebook.com. Will that work? Now, in this case, it should just flat out reject it, and that will be the pass. Oh, Picard, you shouldn't be there. This is a success because it was rejected. So that's good. Now, there's a few other edge cases I want to test. What about, go back. Yeah. So what about pushing a 404? Because sometimes we might push content that doesn't exist, and we didn't realize it because of some miscommunication. If I did a push, in this example here, and now we're starting to push down the list here, it accepted the 404, which is interesting because in this case, I had a no store on the content. It was a 404, but a no store, telling the browser, try again if you can. So this is actually good news. So if you're going to send errors accidentally or intentionally, the browser's not going to continue to hit you once it needs to process that content. It's going to use it as you sent it. So you aren't going to create this amplification problem. So that's good news, at least. Now, come back. And at least we do have consistency, except for Edge, which again, XHR calls, it does not trust any XHR calls or APIs for pushes, which is unfortunate. The last thing I want to test is, well, what happens if I have something in my cache, and then I try to push that same content? Now, this is where we start to see more challenges come out. And, oh, come on. Connections? All right. And you can see here at the very bottom that it failed, meaning that the browser accepted a push for something it already had. It didn't say, hey, I don't want it, reset the stream. And unfortunately, this is the case for all of the environments. That they all don't honor, they don't look at the cache at all. They just blindly accept whatever you're sending. So this brings us to I want to highlight a few implementation notes as we look at this. So first off, we talked about XHR calls. There isn't any mechanism for you to acknowledge any pushed content. That is, if you're waiting for a JavaScript API to say, just tell me when I got something pushed, there isn't an API like that. And also to highlight that Firefox uses an initial congestion window for pushed resources at 64K. But the push for cached items is going to be a problem. If you're pushing things and you've got a generic policy, you're going to push the same kind of stuff. So if you were at the talk yesterday, you would have seen both times with Yoav and Kazahu's talk that they were highlighting the possibility of cache digest. This is something that's going to come. In the meantime, you're going to have to manage it with cookies. Identify what stuff you've already pushed, and be able to just remember that and go from there. All right. So the last thing I want to talk about is, well, we know which browsers support it. We know that we can at least push content that's on my domain, and I know that I can push my APIs if they're on domain for the most part. What about my opportunity? Well, should I be pushing? Is it going to work or is it not? Now, you may have seen Facebook talk about the success that they've had with pushing content. At the same time, you may see comments like from Sam that say, you know what, H2 is not going to work. The world's going to collapse. So I'll highlight that we are on this, probably kind of come into this trough of disillusionment fairly soon here about HB2 push, because it is kind of hard. So let's talk about how we're doing it today. There's basically two different models. There is the push late by sending a header on the response using the link header. So you can see here the link for jQuery using the rel equals preload. But in an example here, you can see what happens. The HTML gets sent. The user had to wait nearly 4 seconds for the first byte, and then they get pushed CSS, but the CSS finishes before the HTML comes across the wire. And this is because that while we're trying to improve the number of packets that we're getting to the browser, what we've done is we've intermingled our HTML, and we've actually delayed the response. We still have missed our opportunity. And really, it's all because of the headers. The headers that you send back are too late. They come only after you're ready to send data. Even if you're going to flush your headers early, that might help, but there's this nasty issue of the status code. What happens if there's an error that actually occurred in your calculation of, you've already committed to a status of 200, and now I've sent my link headers, but I need to change the status. So again, there's a proposal to help address this. Who has got the status code of 103, a mulligan, if you will. Here's some headers. I'm still going to process the page and let you know when it comes back. Now, the RFC was fairly clear when they were putting together Promise. Their intention was you shouldn't be doing promises unless you have time between serving the response. So if you're using Jetty or H2O or Akamai or others, you can set up you can programmatically define when and what resources to push, which is great. This allows you to use that time in the margins and really do get the time before and use it great. But what happens if you push all of it and send that to the kernel too soon? You can still delay that HTML because now you've just been pushing JavaScript and CSS blindly, and you put your HTML at the end of the queue. So let me show you some real-world data. Here is I've got 2 sites I'm going to show you with CDFs running 1,000 times through each, and what happens if you push different content. And this is the original shape of the curve. Now, if you push just the JavaScript and CSS, and it was just enough, you can see that my curve moves to the left. So that's a good sign that it basically got faster for most people. However, if I pushed my images, which took up a lot of time, a lot of bytes, my CDF moves to the right, which is the wrong decision. And similarly, if I pushed everything, the HTML catches up, but it's still committed. It's still going to take a longer time to display. And similarly, on a cosmetic site, I'm going to run you quickly. Pushing just JavaScript and CSS moves it to the left. If it's enough of a window, you can see that there's this overlap period right around the 20th percentile where it was fast already, and so by pushing JavaScript and CSS, I'm actually slowing it down a tad. But generally, it's OK. But if I did images, it'd be terrible. If I pushed everything, it's also terrible. Now, the reason for this is because of the content that's being pushed into the kernel. If your server is doing any work and it says, oh, I've got to pick up some JavaScript and CSS, it can now flush that to the kernel really quickly and send that data. Now, once it's committed to the kernel, that is out of the user space. You have no control over how much data is. You can't go back and say, you know what? I know the user hasn't received all the data. Could you just put this HTML in the middle of it? You don't have that opportunity. And this is why, if you look at Google's recommendations for using push, it's mostly focused around using the time window that you know you have. So if you know statistically you've got 500 milliseconds, then just push enough content that the average user would benefit from it. Well, that's great, but there's a lot of places in the world that are different than your user experience. You know that if a user in the middle of the night in Tokyo is making a request for your site, is going to be different than a user here in Amsterdam making the request for the site. Just the laws of physics. But you also know that sometimes your servers get a little sluggish and somebody doesn't notice until the next morning. It's just a little slower. And you also know that sometimes you get hit with load. And there's a lot of different reasons, including third-party content that might be blocking, that your content, that it might not be consistently 500 milliseconds. It might be wildly variable. So to address this TCP head-of-line blocking issue, yet again, an awesome guy has been working hard at this. And he's proposed using different techniques and only flushing to the kernel just one C-wind width of data. So that way you can adjust what you've been flushing to the user. And by doing that, you do then, because it's in user space, be able to reorganize the content. So this is something on the responsibility of your HTTP stack. If you're using a CDN or whether you're building it yourself, this is the kind of thing that you can do today and take advantage of. But the service provider should be bringing that to you. So what I wanted to show you is the complementary to can I push is the should I push. And what this tool does is it really just takes web page test results. And you punch in that web page test, and it will draw you a graph, bandwidth graph, and then highlight in different scenarios what is the waste of time. What's the opportunity missed that you could have been pushing out content? And so the idea here that I want to help you with is run it through different scenarios of different latency, different parts of the globe, and see how much time you could have been capitalizing on by pushing content. Now, there's two things I want to highlight. First is the time to first byte. But there's always this moment, this little lull while the browser figures out what it wants to do once it gets its pre-parser running. And there's also that opportunity can also be used to push other resources while we're waiting for the first resource to come back. So time to first byte and time to first resource are the two things that I would be highlighting in here. Just to quickly show you what this will look like. So if you see at the bottom here, the red is the time to first byte, is the opportunity missed. Let me see if I can zoom that in for you. While the orange is the opportunity time to first resource, while the blue is the calculated. So I'm using the resources from web page test to calculate what the bandwidth of the browser was using. Now, expect to see iterations over this over the coming months. But I want to give this tool to you to see you can experiment to see how much could I use and benefit from HTTP2 push. Now you can also play with setting the RTT and also using delayed acts, which delay the growth of the C-wind. All right. So let me come on back. All right. So one last thing, there's a number of other questions and predictions that we need to address when it comes to HTTP2 push. One of them is around client hints and session cookies. If you depend on these resources early, well, the resources you're pushing won't have access to client hints because they require the browser to opt in. And if the browser hasn't gotten that far in processing it, you won't have access to those session cookies or any client hints. But I think there's some opportunity here when it comes to cache management and even next page, if you can predict the next page and push content for that user. There's actually some interesting security discussions around could you use push for malicious clients and start throwing at content that's too large for them and just make them really busy for a long period of time. I don't know how effective that's going to be, but interesting conversations. So for you today, what should you be doing? Well, first off, if you are using any kind of optimization methodology in your organization, just cache everything. If you're caching everything, your time to first byte is going to be right down to as low as possible, and you won't need to use push at all. So cache, then you don't need to use push. But if you can't, look at other parts, especially third-party content. That's going to be competing for the processor time, and it creates more window for your browser to be pushed content. Move your content, your JavaScript API calls, move them on domain. While we know that some browsers don't allow for pushes of those API calls, by putting them on domain, you've increased the probability that pushes will be used. And for those browsers that do support connection coalescing, at the very least, bring all your certs to on the same certificate. And then finally, experiment. Experiment with should I push and can I push, and test your websites globally. So with all of that, I want to thank you very much for your time, and I'm open to some questions. Thank you.
Any questions?
One guy back, right there. He's just looking for a book. He's going to ask, what is your name?
So as for deciding which content gets pushed for each request, I don't think many developers are looking to configure that for this endpoint, it's this request, for this endpoint, it's this content. So are there any plans that for example, for CDN-backed endpoints, that you kind of measure that, okay, for this request, it's often these resources that are getting pushed back, so I'm going to push those ahead and keep track of which are too many?
I'll pay you your $10 on the way out. Yes. So this is absolutely you've highlighted the issue of doing manual configuration for pushes because A, it needs to be maintained, and B, it needs to be accurate, and it's easy to get those disconnected. And I can speak for Akamai, the company I work for, but I'm sure it's going to be fairly that we are heavily invested in using analytics and doing that automated measurement and realizing that that window might be different for you in one geography versus another geography, versus mobile versus desktop, that this page versus another page. And I believe that's going to be the new frontier, is using analytics as a means to intelligently figure out how to use that time in the margin. Awesome.
Anyone else?
Oh, two questions right back there.
Is it essentially manually pushing in conflict, or maybe not conflict, but in competition with prefetching using links in your header? Isn't that much easier?
Yeah, well, so you're running into two challenges when you're using links in the header. One is you're competing on the TCP stack and pushing content when you could be pushing HTML. And the second is you've got the browser, which can also be doing things and deciding maybe that the stuff in the link is not as high priority as something else, perhaps it's discovered. Now, it will adopt the stream that you've been pushing, so you don't have to. There are some race conditions in there, but you should be using that surgically. I don't generally like the idea of using the link header because of the time in the window and when you're sending it. It's going to be better to use the full window, full time to first byte. That's where the real opportunity is, and not getting into this race condition.
Gotcha. Thanks.
We had one more back here.
There's a couple back, the very back of the auditorium. While waiting for her to go there, my wife made a cake.
Nice cake. Thank you for the talk. I was wondering, why doesn't the HTTP2 standard include something like cache digest? Are we using it wrong than it was envisioned a couple of years ago, or did they want to keep it open intentionally to see what we would do, or?
You know, as far as I recall, it was discussed, and why it wasn't adopted is more pragmatic reasons. There's a lot of concerns around security and around, you know, are you going to be leaking data that you shouldn't be sending to different people? And this is where the challenge is. And there's been a number of iterations on the cache digest. So we're still evolving that to satisfy a lot of competing concerns. So HTTP2, as far as I recall, wanted to get something out rather than solving all the world's problems. Let's solve a set of them, and it's a very pragmatic reasons.
Unfortunately, we are out of time for questions, but I wanted to thank Colin very much, and our next talk will be up at 2:40.
Thank you.